in F-star. This is day 6. We'll get started in a few minutes here. I'll just send out a tweet about the live stream. So welcome, happy Advent. Not sure, did Hanukkah just end or is it the last day of Hanukkah? I'm not entirely sure. But it is the 6th day of Advent of Code. We're 5 for 5 on this channel so far. I don't know if this will be the day when our streak ends. Let me pull up the F-star page. Start screen sharing. So I'll be using a language called F-star. It's a general purpose functional programming language that has dependent types. This says with effects, but I got into it because it had dependent types. And so it's for proving things about your program and having those proofs formally verified. So you can say, this function not only returns an int, it returns an int that has a particular relationship with the argument. So it returns an int in a particular range. And so we can use that to sort of, boost the effects of static type checking by creating more complicated types. My employer, Akita Software, is a sponsor of Advent of Code this year. We've got some job postings up at akitasoftware.com/jobs. I'd love to have you talk to us about working for Akita. We're building tools for API observability. All my solutions are up on my GitHub page at mgooder/AOCFstar, as well as some documentation I've been doing for myself, some links to resources about F-star. Let's pull up Advent of Code. Got about a minute left, minute and a half. Oops. So last night I finished in about an hour and a half, so that's good. I didn't want the 2-hour 20-minute trend to continue. But the rank was actually the best ever on part 2. So most of the work was in getting part 1 done last night. I really didn't have any follow-ups. I was pretty happy with the part 1 solution, with the solution from last night, except for a couple things that I couldn't figure out, like how to. The big surprise was F-star doesn't have a way to count the cardinality of a set. So I looked into that a little bit, and I could add a function that binds to the OCaml implementation and did that. But I haven't done that yet. I'm hoping today we do not have to use a ordered map or an associative array, because the one F-star provides is linear time, unfortunately. So I've been looking at the B-tree implementation in the examples directory in F-star and modifying it so it takes a value. So if we really need an ordered collection, we can finish that. But I'm hoping we don't need one for today's problem, where we can get by with a vector. And we're off. Okay. Okay, so our lanternfish spawn every 7 days, and then a new lanternfish need 9 days. And says, well, we can represent that as an internal timer. Okay. Okay, so these are the timers of the fish, the countdown to producing a spawn. Okay. All right, so we're asked to simulate this. And the hint given here says, I think is a little misleading because we're not going to create a 5,000 element vector. We're just going to want to record how many there are in each state. So let's do that. So we can copy our integer parsing code from yesterday. Let's just copy those. Okay, so that given a string parses it as a list of numbers. Okay, so let's create a type for fish population that is a vector. Did I pull in vectors? Is that from a previous day? Okay, so this was my own implementation. So it's a vector of natural numbers, and they're bounded by 8 or by 7. They're bounded by 8. So it starts okay, yeah. And oh no, that's the wrong value. We've got 9 different values, 0 through 8. All right, start that all. Start up. Okay, we didn't import. To import the list functions. Okay, we're good. All right, well, let us write the function that takes one fish population to the next state. Call it fish step from one fish population to the next. All right, so can we say anything about this? You know, there are a lot of things we could prove. So why don't we write a lemma afterwards? It's not clear what type we'd want on the return value because there's a lot of different things we could say. Okay. So this is sort of Markov model-y. I think the simplest thing is actually just write them out. So anything with a timer value of 6 oh, okay. So anything with a timer value of 1 becomes 0. Anything with a timer value of 2, this is 0, 1, 2, 3. Am I getting that order right? Yes. All right. Again, I'm counting things correctly. All right, so 6 is special. That's the fish that did have a timer of 7, as well as those who had a timer of 0. So 6 prime is zero. So 7 is just the fish that are old, that were 8. All right, so the ones that are of length have a timer value of 8 are created from those who hit the timeout value. So I think that's all required. Does it type check? It's not, because it doesn't know how long it is. All right, we figured out how to deal with that earlier. We just assert and that should be sufficient to, yeah. All right. So let's prove something about it. Imagine all top 100 places are already gone by now. This is a fairly easy puzzle, I think. All right, let's start easy. If all the fish are extinct, then the new step population should be 0. So let's do one more thing first. I think we're asked to do the total number of fish. Yes. Okay. So let's write the sum function. I'm kind of surprised we don't have that already, but so we need to fold left with the plus operator. Which way is left? Okay, good. All right, so we're going to say if total fish P equals 0, then can it automatically prove that? It cannot. It might be able to if we had written this out in full. So, what can we do here? We can't really do induction on the fish population as such, but we can do it on a list. As a matter of fact, it's not true because we didn't specify that the number of fish had to be positive. Oh no, we did. It's a vector of natural numbers. So let's in fact. All right, it's going to make it difficult for us because the plus operator works on natural numbers on integers, I mean. So we have to tell it, no, we're really just adding natural numbers, which is sort of a pain. All right, still can't prove it. All right, but at least I think so. Let's see. I wonder, based on okay. So we know that's true. All right, so let's prove that. 0 if all zeros, and we'll prove that about an ordinary list of integers. So if index of I requires induction, so let's just write induction. I learned today that F star has a piece of syntax from OCaml, which is you can just, instead of doing a function that's just a match, you could say function, and function has an unnamed argument and applies a match to it, all in one. So we could write the lemma this way. Lemmas in F star are just functions with funny types. Lemma itself is just syntactic sugar. Okay, so match P with, it's an empty list, then that is truly true. Otherwise, let's see if we can figure it out based on just that. So let's find this as a, Right. So it's telling us that it doesn't know that the sum of that. All right, so assert. Does it know that? Is there a lemma about folding we can appeal to? Lots of lemmas about fold left, and I don't know how to use them. All right. So this says got some property that's true. I don't like that. All right, this says folding left of a list, pair of lists is the same as the concatenation list, the same as folding left and then folding left again. That's pretty close. Let's try that. So some lemmas are introduced automatically based on pattern, but this one is not. And the trade-off there is the more things you introduce automatically, the harder the let's introduce this. The harder the SMT solver has to work. There's just more state in its buffer, in the model that F-star sends to it. Left append, add, head, tail. All right, I'm going to put that on hold. I can't even prove basic things about it, I guess. All right, let's grab our input and run for, okay, well, let's write that function. So we're going to run the fish population for n steps. So if n equals 0, then p else n minus 1 fish step. It feels like we should have a helper function that does that already, something like fold left but iter end, but I don't know of one. I didn't see one anywhere, but that's no guarantee. All right. So where's our input? Okay, yeah, we're going to have to translate this into our format. So write that. So we're just going to do the Taylor recursion again. So we've got a list of natural numbers. We didn't guarantee that they're natural numbers. We guaranteed that they're integers. Okay, we can handle this. Okay, so if head is less than 0, then we'll just skip it. Else we're going to I don't know if we have the right function for replacing. Well, it's kind of silly to have to write. Partition, subset, split. Okay, this should do. Okay, split 3. Split the list into 3 parts. So 4 and after. Okay. You have to cover both too little and too large. Split 3 of P at index given by head, which is the state of the fish. Set new population equals before okay, it's complaining that it doesn't know head is the right length. Let's oh, all right. Okay, so it doesn't. it should know that the length is okay, what's going on here? I think alright, does split have a lemma? Let's try proving that. Alright. So we're going to take a list of integers. We're going to take a position in that. That's what split3 did. And we're going to take a replacement value. Okay, this could be a list of nats. Alright, it's better to just spell out as many things in the arguments. So for this after split, alright, so it requires split3. Does this even work? I haven't been using this before. I've been using selectors, but I guess it worked. Alright. Li equals before bridge after. And we want to ensure that for that wind's really blowing out there tonight. Right. I can't prove it, but that's fine. So what can we recurse on? Well, what do we need to know? All right, so this definition itself uses a lemma. Okay, so the first version of this as well. All right, let's try this at least. So we've got so that gives us that the length of before equals that gives us the length of after. Guess it doesn't. Which is most inconvenient. And it's always someplace I don't expect to get tripped up. There we go. That is probably what the problem was. Okay, so both these assertions are true. All right, so append length. Oops. We're still missing something. So we told it it should be smart enough. Those. Okay, we don't know how long before is. Do we? We don't. All right. So I think we're going to need a lemma. About split's first length. Where was that? Was that over in base? It was. All right. So we're saying the length of the first split is n. I didn't get it right. All right, so it's our inductive case. Oh yeah, of course this doesn't work. All right. So. Did I even change the lemma name? All right, there we go. So. Hurrah! All right. So we pull in our lemma here. We say, so we had P, we split it at HD, we replaced it with n plus 1, before and after. And we're good. All right. That was an awful lot of work to prove that our list was the same length as it was when we started. All right. So So let's create a helper around that and start with the 0 population. Seven, 8, 9. Okay. Additional population equals list. Okay, so we open the file, we read in the numbers, we calculated, and then we're going to do fish step n, and let's do the example first. Example had 18 and 80. Sure, so let's 18. We do some work, it should be fine. And we just have to print the total output, the total numbers. Oh, we need the sum. Okay, let's grab that. Okay, those numbers match. That's a good sign. Let's do it for the whole input. All right, let's see what it thinks of that. All right, just ask us to do 256. Okay, does our test number match? Looks like it. I'm disappointed, this isn't a very big number. All right, that's both stars. I imagine since I wasted a bunch of time proving things about taking lists apart and putting them back together that we do very good today. Oh no, rank 6,000. I guess a bunch of people did it the inefficient way first. All right. So I would really like to at least prove something about a transition function. Maybe you should do something easier than this. All right, so let's start out with something really simple. We know head plus equals sum p. Is that true? It doesn't even know that. Why is that? I have no idea what these lemmas would be used for. So this one says these requirements seem very odd. We do have a monoid. Operation under addition is a monoid. So we got op and a 0 and a list. These are the conditions on a monoid, and they are true. Then, okay, I think that's what we need. All right, so let's use fold left monoid, and it wants our operation, which is natural addition, and our identity element of, so that's our monoid operation is addition. 0 of the monoid, the identity of the monoid is 0, and our list is P. It still says it's not true. Okay, let's do head and tail. Okay, what did that monoid give me? So I'm gonna change this to assert by tactic, and we're just going to give it a tactic that doesn't do anything, just prints, dumps out the environment, so we can see what I need to reload. Oh, phooey. It's got its own fold left. Alright, so star this go. Okay. Net add of for all x, it says that is true. That should be true for head. Yeah, it's not quite what we proved here. Yeah, we proved that adding using x as our 0 element is the same as adding x outside. Okay, so that says that the sum it's mainly just a matter of matching things up so that F-star has all the pieces it needs. So it's got the definition of sum, it's got the definition of fold left. I wonder if this would be easier if we did fold right, but no big deal. Okay, so we could use this with x is our, so assert sum so head and tail equals head plus sum of tail. Okay. Okay, so we got past that. Good. So it should be the case. Oh, I gotta wait for it to time out. All right, so we should know that Right, it knows that. So it must be the case that both head and sum plus TL is 0, which is all we need, I would think. It might be just timing out because we're using index. Okay, let's try this. So I think it follows that both these are 0. And it agrees. So if the sum of the tail is 0, then we can recursively apply this. So, okay, so the problem is it probably doesn't know how the index alters as we build the list back up. And there should be something. All right, let's give it some more time and see what it does. So set option. So can we rewrite this a different way, not using index? Could we say we could just use list for all? That won't work. Or number. All right, let's try that. For all. For all. Expected list. Oh. Gosh, why is it failing? All right, so we know it's true for everything in B0, and we know it's true for head. So why don't we know might go better if we give it a name. Okay, so cert. So that should be it. We know, I mean, there it is on the right-hand side. B and B0 is B. So is there a problem with the base case now that we switched it? No. I'm very puzzled because it seems to me like we have proved everything we could possibly need to prove this. And yet not able to draw the dots. I'm hoping if we give it more time, it'll give us a more specific problem. But the annoying thing is if F star fails, it tries again with more fuel. And fuel is how F star controls how deeply does it unfold recursive functions. So by default, it only puts the definition in, but it could also put the definition and the definition nested inside the definition, and the definition nested inside the definition inside the definition, and just create bigger versions of the functions to reason about. And I guess my experience has been that hardly ever helps, but it's set up by default to run with the low version the first time, and then if that fails for whatever reason, try again with the larger values. So I'm puzzled because it sure looks like the type we have from the tactic is there, and if it's there, then you know, we've proved the lemma. So all right. Okay, so it says it was actually this one up here that was failing, which is a little odd. We used a monoid property incorrectly. No, let's get it for all. So yeah, just if we look at that, filling in X with head. Oh, okay, but we only proved it for this particular one. So we need to do it. We need to do it just on the tail. Let's try that. All right, that was the problem. I used the limit incorrectly. All right, so let's clean this up. Those two in. Okay. Yeah, so the limit was correct, but I was calling it with P, and so it was proving this for all statement. It's probably a little small on the screen for you guys. About the entire list, and we wanted to prove it just about the tail. All right, so okay, so let's use for all. I'm going to use our lemma. Okay, so that tells us this would be a great way to use the time to use a tactic. To actually loop in all those assertions, because I want to tell it that it has to use that universal. Okay. Fails. What should that be? Length is 9. That's really very odd. Yeah, this I sort of expect. So we haven't. This might actually be a case where we need to unfold more. Let's give that a try. Yeah, okay. So this is the rare case that actually does help. So we told it to unfold 10 times, and that is enough to get index to the end of the list. Don't know if there's a better way we could do that. Oops. But then once we did that, then it's actually able to prove, okay, good enough. Then it's actually look at the definition of fish step and say, okay, that's just math, I can do that. All right, so I'm happy we proved at least one thing about our code. Usually when I sleep on it, I can think of a better model for correctness. But this is really so simple, it's going to be hard to say anything meaningful about it. Like we could show that, let's try showing it always, if it's non-zero, it always is monotonically increasing. We could show that. I don't think that would be very interesting, but would probably be almost as hard as proving this. We'd have to show that I don't know. Anyway, I will stop the stream for today. We did pretty good at writing this. We got caught up on how do we increment just one element of our list. There wasn't a nice just change one value like if it was a map. So maybe if I'd used the map type throughout instead of the list, then that would have been better. Or maybe if I had not used split 3, because we had to go use the lemmas that were from just the normal split function anyway. And we had to write a new one. So maybe those will be helpful later. This one seems like an odd omission from the standard library. Because we got the one for the second saying how long it is, and it doesn't automatically, I think, know how long the first is. That if we get rid of that, then as I recall, this one doesn't. Yeah, it doesn't know that. Okay. Well, good night. Happy Advent. See you tomorrow.